Hello, and welcome back to another IB Math speedrun with me, Vince. In this speedrun, we're going to be going through modeling real-world scenarios using differential equations. So let's jump right in. So the general model, like for a logistic equation, usually looks something like this: dn over dt is equal to kn times n, kn times a minus n, where a and k are real numbers, and t is the time during which a population grows, n is the number or the population after the time, k is the relative growth, and a is a constant. And so this is just a general form. You don't need to memorize it, because more often than not, the problem will actually provide you the model you need to use. So let's jump right into some questions. So we'll do the even ones, and so the first one we have is industrial oven is kept at a constant temperature of 180 degrees Celsius. A chemical initially at 0 degrees is placed in the oven. The rate of increase in temperature of the chemical is proportional to the difference between the oven's temperature and the chemical's temperature, T. After 5 minutes have passed, the temperature of the chemical is 120 degrees Celsius. So first, find a differential equation that models this problem. Secondly, determine the temperature of the chemical after a further 5 minutes in the oven. And C, oh, that's it. So what we can say is chemical 0 degrees, temperature of the oven. Okay, so the rate of increase in the temperature of the chemical, which is dt over dt, is proportional to the difference between the oven's temperature and the chemical's temperature, T. So it's K times the oven's temperature, which is 180, minus the chemical's temperature, T. And after 5 minutes have passed, the temperature of the chemical is 120 degrees Celsius. So this is a differential equation that models the problem. And we need to find out what K is. Actually, can we just solve the differential equation? 5 minutes have passed. Okay, so let's try and solve this. So we get 1 over 180 minus t dt is equal to k dt. So we have ln negative ln 180 minus t is equal to kt plus c. Oh, the temperature is initially at 0 degrees. Okay, so we can solve now for this. So let's solve for k first. So, I mean, it doesn't matter. We have two linear equations. So first, negative ln 180 is equal to c. Okay, so that was pretty simple. So this is negative ln 180. and we need to solve for k. So we can use additional information that they gave. That's after 5 minutes have passed, the temperature is 120 degrees Celsius. So we have negative ln 60 is equal to t is in minutes. So we just say 5k minus ln 180. So we end up with ln 180 minus ln 60, which is ln of 3, is equal to 5k. So k is equal to 1/5 ln 3. So we have negative ln 180 minus t is equal to 1/5 ln 3 times t. So 1/5 t ln 3 minus ln of 60. And so we don't actually need to rearrange this to get it in terms of t. We simply need to determine the temperature after a further 5 minutes in the oven. So if we add 5 minutes, so we get 1/5 times 2, so this is 2 ln 3, minus ln 60 is equal to negative ln 180 minus t. So ln of 180 minus t is equal to ln 60 minus, this is ln 9. So is equal to ln 60 over 9. So 180 minus t is equal to 60 over 9. T is equal to 180 minus 60 over 9. And 60 over 9 is equal to 20 over 3. So wait, this is over 3? Why is it over 3? Oh, this is ln 180. Oops. Anyways, ln 180, ln 180. And so ln 180 over 9 is equal to 20. So we have ln 20, so 180 minus t is equal to 20. So the temperature, the new temperature is 180 minus 20, which is equal to 160 degrees Celsius. So that is the answer. On to the next problem, where we have the rate of growth of a population P is proportional to the size of the population. A culture of bacteria in a lab has an initial population of 500, and after 3 hours, the population has grown to 10,000 bacteria. So first, write a differential equation to model this problem. Next is to solve the differential equation. Next, find the number of bacteria present after 5 hours. And finally, determine how many hours are necessary for the number of bacteria to reach 500,000. Okay, so rate of growth of a population is proportional to the size of the population. So dp over dt is equal to some constant times p. And so this is enough to model it, I think. So now let's solve. So we have 1 over p dp is equal to k dt. So we have ln p is equal to, this is kt. So the population will be equal to, plus c. So this will be equal to e to the kt plus c. So solve the differential equation, done that. So we need to plug in these values though. Initial population of 500. So when t is 0, actually, okay, no, this is correct, actually. So, but we can also rewrite this as e to the kt times e to the c. So when the population is 0, when time is 0, population is 500. So we get that e to the c is equal to 500. So we can just simply rewrite this as 500 e to the kt. And when the population, after 3 hours, the population is 10,000. So 10,000 over 500 is equal to e to the 3k. So 3k is equal to ln, what is this? 20. So k is equal to ln 20 over 3. So we can model this as the population is equal to 500 e to the ln 20 over 3 times time. So next, what we need to do is find a number of bacteria present after 5 hours. That's simply 500 e to the 5 ln 20 over 3. Oh, 5/3 ln 20. And so, what is 5? Which is 500 times 20 to the power of 5/3, I think. Yeah, so this is around 73,680, around this value. And the next, determine how many hours are necessary for the number of bacteria to reach 500,000. So we have 500,000 over 500 is equal to e to the ln 20 over 3t. So we have ln 20 over 3 times time is equal to the natural logarithm of 1,000. So t is equal to 3 ln 1,000 over ln 20. And this is probably a decimal. So let's put into the calculator 3 ln 1,000 divided by ln 20. And we got something like 6.91 hours. So you need to exceed this, you need at least 7 hours. Okay, on to the next one. And the next question is, on the first day of school, after a break, one student comes to school having been infected by the flu. There are 100 students in the school. The rate of spread can be modeled as dn over dt is equal to kn times 100 minus n, where n is the number of students infected after t days. First, solve the differential equation. It says show that the solution equals something. I'll put it run. If on day 1, student was infected, and on day 2, 2 students were solved the equation. See, solve the differential equation for n and determine how many students were infected after 1 week. So we have dn over dt is equal to k times n times 100 minus n. Okay, so we can simply put this as 1 over n times 100 minus n is equal to dn is equal to dk dt. Sorry, I'm back. So I realized that we actually have to decompose this into partial fractions, which I should have realized a lot earlier. So we know that we can arrange this into something like a over n plus b over 100 minus n. So we have 1 is equal to a times 100 minus n plus b times n. So 0 is equal to negative a plus b, and 1 is equal to 100a. So a is equal to 1 over 100. And b is also equal to 1 over 100. So this will be equal to 1 over 100. The integral of 1 over 100 times 1 over n plus 1 over 100 minus n. And this is equal to the integral of k, I believe. Yep, k dt. This is dn. So when we integrate this, we can simply do ln n plus minus ln 100 minus n is equal to 100 kt plus c. So we can write this as ln n over 100 minus n is equal to 100 kt plus c. And so we have n over 100 minus n is equal to some constant a times e to the 100 kt. Since remember, if we're raising e to the c, it's equivalent to having a constant at the front. So that's what we needed to prove it equals. Next, if on day 1 1 student was infected, and on day 2 2 students were infected, find a and k. So substitute the 1 in. So 1 over 100 minus n is equal to a e100 k, and 2 students on day 2, 1 over 98. Sorry, 2 over 98, I mean, is equal to a times e to the 200k. So we can solve for either first. I'll solve for a. No, it's also for k actually. So we have 2 over 98 e to the 200k is equal to a. So we have 1 over 99 is equal to 2 over 98 e to the 200k times e to the 100k. So this is equal to 99 is equal to e to the 100k over 2. So 2 times 99 is equal to e to the 100k. So 100k is equal to ln 198. So k is equal to ln 198 over 100. which should be equal to around 0.0. That's different. Have I made a mistake? 99. Oh, I forgot about the 98. That's why. This is equal to 2 times 99 over 98. So this is actually ln 198 over 98. So this should be equal to ln 198 divided by 98 divided by 100. It's equal to around 0.007. So that's k, and now we need to find a. We can do that by substituting this back into one of the original equations here. So we have 2 over 98 e 200 times 0.007. So we have e to that times 98, and so we have 2 over that. So I'm getting that a is equal to around 0.005. So a is around 0.005 and b is around 0.007. I mean k. So finally, we need to solve find how many students were infected after 1 week. Solve the differential equation as well. So we know that n over 100 minus n is equal to 0.005 times e to the 100 times k, which is 0.007. So to e to the 0.7t. So we have n equal to 100 minus n to the power times 0.005 e to the 0.7t. So we know that n times 1 plus 0.005 e to the 0.7t is equal to 1. Well, multiply this 0.5 e to the 0.7t. So we have n is equal to 0.5 e to the 0.7t over 1 plus 0.005 e to the 0.7t. And we can evaluate, we can change this a little. Can we do e to 0.7? Yes, we can actually. So this is actually equal to 0.5 times 2.01 to the t over 1 plus, because we can raise e to the 0.7 to the t. 1 plus 0.005 times 2.01 to the t. And then if we multiply top and bottom by 100, we can simplify this into 100 times 2.01 to the t over 200 plus 2.01 to the t. So to get how many infected after 1 week, let's substitute 7 in. So we get 100 times 2.01 to the 7 over 200 plus 2.01 to the 7. So this is equal to the 7, so 100 times this divided by 200 plus this. And so sorry, I need to do this again. 2.01 to the 7. 100 times that amount divided by this amount plus 200. So I get around 39.8, which is around 40 students would be infected by this point. So yeah, let's move on to the next question. So the next question is, in a village, the rate at which people are infected by an epidemic per week after the outbreak can be modeled by the logistic equation dp over dt is equal to 0.8p times 1 minus p over 350. At the outbreak of the disease, 7 people were infected. First, we need to solve the initial condition problem for p, and then next we need to estimate how many people in total will have been infected by the disease. Okay, so we have dp over dt is equal to 0.8p times 1 minus p over 350. So yeah, we can solve this pretty easily. This is 1 over p times 1 minus p over 350 is equal to 0.8 dt. So we need to split this into partial fractions. So we get 1 is equal to a times 1 minus p over 350 plus bp. So we have 0 is equal to negative 1 over 350a plus b, and 1 is equal to a. So b must equal 1 over 350. So we have the integral of 1 over p plus 1 over 1 over 350 times 1 minus p over 350. So this is equal to 350 minus p. dp is equal to 0.8 dt. So we have ln p minus ln 350 minus p is equal to 0.8 t plus c. So we have p over 350 minus p is equal to some variable, say c times e to the 0.8 t. So at the outbreak, 7 people were infected. So we have 7 over 350 minus 7 is equal to c, and then time is 0, I believe. So c will be equal to 7 over 350 minus 7 is equal to around 0.02. So we can rearrange this a little. So we get p is equal to 350 minus p times 0.02 e to the 0.8 t. So we have p is equal to this would be 350 times I think 0.02 e to the 0.8 t all over 0.02 e to the 0.8 t plus, is it just 1? Yeah. But then we can convert this by multiplying everything by 0.02 into 350 times e to the 0.8t, and e to the 0.8 is 2.22. This might be e to the 0.8 actually. Yeah, sorry. So I think this is day 1 of the outbreak. So this is 7 over 350 minus 7. So 0.02 divided then by e to the 0.8. Yeah, and so we get c is equal to around, not 0.02, but actually it's around 0.009. So we have p is equal to 350 times 0.009. But I think they've made a mistake. I think the books made a mistake because they've multiplied 0.02 to the constant, which is incorrect. This should just be they've made the mistake. This should be 350 times e to the 0.8. I mean, not 0.02, I mean 0.009. So this is 350 times 2.23 to the t over 2.23 to the t plus 1 over 0.009, which is equal to around 111. So that's weird. Yeah, I think the book's a bit wrong. So estimate how many people in total will have been infected by the disease. Well, we kind of want to get the limit of this as t goes to infinity of 350 times 2.23t over 2.23t plus 111. And this should just tend to 350? Since because if we divide everything by 2.23t, we get 350 over 1 plus 2.23t over whatever number we have. Sorry, I mean 111. 0.1 over 2.23t. And so as t tends to infinity, this tends to 0, so this tends to 350. So 350 people will get infected in total. Okay, and so on to the final question. And we have the acceleration of an object given in terms of its displacement is equal to a equals 2s over s squared plus 1 meters per second. So first, if the acceleration is equal to v times dv over ds, find v. Given s is equal to 1 when v is equal to 2. So we'll do this part first. So, okay. Find v. So we have 2s over s squared plus 1 is equal to v times dv over ds. So we have v dv is equal to 2s over s squared plus 1 ds. So this is equal to 1/2 v squared is equal to ln s squared plus 1 plus c. So we have v squared is equal to 2 ln s plus c, so v is equal to the square root. And so now we need to get s is 1, v is 2, so we need to find the constant. So 2 is equal to the square root of 2 ln 2 plus c. 4 is equal to 2 ln 2 plus c. 4 minus 2 ln 2 is equal to c. Do we need a numerical answer? Perhaps. No, we don't. It's just 4 minus 2 ln 2. So we have b is equal to 2 ln s squared plus 1 plus 4 minus 2 ln 2. And next, we need to find the velocity when the object has traveled 5 meters. And that's okay. We just substitute 5 into there. So that's equal to the square root of 2 ln 26 plus 4 minus 2 ln 2. So this should be equal to the square root of 2 ln 26 plus 4 minus 2 ln 2. So this is around the square root of 9.12 meters. And so, yeah, which is around 3 meters per second. So yeah, that's the answer. And that is the final problem for this challenge. So that's it, and I hope to see you in the next one.